Hi, my name is Dominic Huskisson, and I'll be presenting my research today titled An Agent-Based Approach Towards Modeling Cost versus CO2 Emission Trade-offs in Multimodal Middle-Mile Logistics. Firstly, I'd like to grab your attention by drawing your attention to a simplified road network map where we have a centralized depot placed at the middle, and it's surrounded by retailers in which it's responsible for servicing, and it has a mixed fleet of vehicles able to service this set of retailers. The mixed fleet would reside at the depot, but for the sake of simplicity, we'll keep it off to the side. And then the novelty of this research project aims to build on the back of Uber-like agents that would reside near to the depot but not at the depot, that also are involved in servicing the retailers. So they would typically reside nearby the depot, drive towards the depot to pick up a parcel, drop off the parcel at a set of retailers, but then they're not obliged to return to the depot, thus saving that leg of the trip. These agents will be represented by the green vehicles, and they will be called courier vehicles. Now overlay this on a formalized map, and we have formalized our problem. Alright, so for this presentation, I'll be going through the case for the solution to outline the need for why we need to solve the problem. Then I'll be going over formalized research aim. Then I'll briefly explain simulation. I'll further expound on agent-based modeling. I'll ground this all in a case study, and then we'll refer to some of the KPIs that we'd like to measure by ending on some preliminary results. So first, the case for the solution. Imagine we have a typical supply chain where our goods start at the raw materials, they travel to the supplier, then to the factory, to our distribution center, to the retailer, and then to the customer. Alternatively, it can go from the distribution center, skip the retailer, and go to the customer. I'll be dealing with the link from the distribution center to the retailer, typically known as middle mile logistics. And middle mile and last mile logistics typically make up about 70% of the logistical supply chain costs. So here's our simplified version that we saw earlier, but in reality, our cases typically look like this, where there's a lot more complexity and a lot more retailers to deliver to, which comprise the majority of the cost of the supply chain. Thus, drawing the attention of researchers to supply high-quality solutions to curb these operating costs. Alright, next, to formalize the research aim. The primary aim of this research is to design a generic framework for providing decision support pertaining to the middle mile delivery logistics of a distributor. And the secondary aim of this research is to implement on a personal computer an instantiation of the framework capable of analyzing the solutions to an agent-based model formulated over a rolling planning horizon. The inputs to the solution is time-stamped commodity demand volumes, time windows, details about a set of delivery modes, data describing the fleets of available delivery vehicles, and thereafter information related to the delivery transport infrastructure. The objective is to attain high-quality trade-offs between minimizing the total operational cost and minimizing the environmental impact of the entire delivery, assignment, and routing vehicle schedule. The decision variables involved entail the vehicle types, as well as the proportion of the various vehicle types. And finally, the outputs entail an assignment of vehicles of the appropriate transportation modes to service the set of retailers, their corresponding delivery routes, as well as their delivery schedules. Next, we'll look at the concept of simulation. So we start off with the picture in the bottom left-hand corner, in which we see the real world. Instead of translating the real world to an improved solution of the real world at a risk of much cost, we rather first translate the real world, model it into a simulation environment on a computer, in which we can trial and error improvements, upon which we can test and validate to see if these improvements hold true. If they do, then we can implement these improvements in the real world. This represents a risk-free way of putting forth improvements. There are various types of simulation environments, namely three here. We've got system dynamics, agent-based modeling, and discrete event modeling. On the left-hand side on the y-axis, there's various levels of abstraction from low to high. We see that something typically like system dynamics is a high level of abstraction where it uses aggregates versus discrete event modeling, typically involving certain events and logical flow of processes, coming more in the medium abstraction level, then agent-based modeling spanning more to low to medium abstraction level, because it allows us to encode individual attributes into each agent, so it allows for a much more bottom-up approach, where each agent has independent and individual attributes that then are encoded to interact with one another, and we are capable of observing emergent behavior and emergent phenomena from agent-based modeling. So just to break down how this looks, we typically have an agent. This agent then has a set of attributes, and you can extend the set of attributes depending on how much detail you want your model to have. And these attributes are typically drawn from empirical distributions, or perhaps they could be distributions found and suggested in the literature. In my model specifically, I've got 4 agents involved. First, we look at the career driver, which has attributes ranging from the vehicle type, age, education, graphical location, availability, and their ratings. Then we can derive further features from combining 2 of those attributes. For example, age and education might be able to give us information about the type of salary the career driver might expect or the wage rate. Then we can look at the employed driver, attributes being the vehicle type assigned and their wage rate. The customer has a demand volume, demand weight, time window, and graphical location. The retailer has operating hours, graphical location, and planning hours. And then important to note that 2 of our agents have the same attributes, their vehicle type assigned, upon which our vehicle fleet has their own attributes, namely variable driving cost, the CO2 emission rate, and average speed and capacity. Now, to begin with the case study, we'll take a look at some of the data that we received on Excel. So you can see here we start off with the geocode, giving the corresponding latitude and longitude, the suburb specifying from which retailer belongs to which depot, the quantity that the retailer has ordered, and the corresponding amount of boxes that that quantity would fit into, as well as the date that order was created. This pertains to just a small sample of the data that was received, but upon which receiving the data, we actually imported it and spent some time trying to understand the data by consulting with the industry partner. In some cases, we added additional features derived from primary features. We then split these features up into categorical and continuous features and conducted a data exploratory analysis on these features, removing any anomalies and missing values or erroneous values, and iterating this process until satisfied with the quality of the data. Also, just to take a brief overview of the data then, the data consisted of more than 204,000 entries over the entire year, split up into 333 operating days in that year, excluding some weekends and public holidays. There were 7 depots delivering 2 distinct regions, so you could cluster the data into 7 different regions, upon which each depot delivers to about 80 to 350 retailers today. So it's clear to see from the size of this data and the sheer amount of deliveries needed per day that it's not solvable optimally in polynomial time. Thus, the solution requires a mean heuristic to suggest high quality solutions. Here is a plot of the data to represent it visually. This is the coordinates of the demand points over the entire year, where each dot represents a retailer's demand on a given day, with the latitude and the longitude on the y and x axis respectively. Of course, from this you can see that there's a vast amount of demand. However, the demand is split up and serviced by various distinct depots in various regions. Here is a display of the various clustered regions, where each color represents a different region, which will be serviced by a different depot. In this presentation, I've further isolated the light green color in the middle, representing a region called Lynbrow, just for the sake of the case study. So if we isolate that, then we see the coordinates plotted for Lynbrow throughout the year. And we can further dilute this and isolate just a single day of that yearly data, in which case we end up with something that looks more along the lines of this, where we have a central depot imposed by the orangey pink square, the central, and with concentric circles coming out of it. And these circles represent the assignment structure of the vehicles to the various retailers, whereby it might be beneficial to assign one type of vehicle to the outer ring and another to the inner ring, like a bicycle would favor serving customers in the inner ring. Beyond that, you can also assign vehicles with a higher capacity to areas that are more clustered, because they're able to service a higher density of customers before returning to the depot. Now that the concept is laid out, we'll just quickly take a brief look at the back-end workings behind how this is achieved. So first we get the data in the form of Excel file, and this Excel file is then cleared and the specific data is isolated that we want to take into our Python model. That data is specifically an N/N matrix, N/N CO2 matrix, retailers and demand volumes, and the specific vehicle capacities. We then implement a saving algorithm and simulated annealing algorithm in Python, upon which the outputs are an assignment of vehicles of the appropriate transportation modes to service the set of retailers, their corresponding delivery schedules, and subsequently the delivery routes. This all gets sent to the AnyLogic environment, upon which it's simulated and we can observe emergent behavior. We now implement the back-end workings on the case study. So this is the first day of data from the Lynbrow region, where the x and y axis are the latitude and longitude again. And we now implement the savings algorithm and the simulated annealing algorithm on this data to suggest assignment of vehicles and their corresponding schedules and routes and to service the set of retailers. The result is a set of routes as follows, where the magenta color represents the retailers that are serviced by the courier vehicles. You'll note that the routes are all enclosed loops, whereby these routes are then suggested to the courier vehicles, which are assumed to be lurking around in the nearby regions close to the depot. And if the incentive is high enough and there's enough value on the trip, the courier agent would accept or reject the trip based on the amount of value that it would add to them. That value is depicted by the comparison between how close the courier vehicle is to the depot in comparison to their final destination that they would end at. And to represent this, we randomly plot agents represented by the black X's in the nearby region to the depot, and this is just a proportion of the original demand data that is able to be specified by the model. And so you can see the corresponding agents numbered 1 all the way up until 20. The courier vehicle's routes, represented by the magenta color, are then offered to the agents, upon which some of them will accept and some will reject, and you'll typically see the agents that reside close to the depot accepting with a higher probability, whereas the others reject the offers made to them. Here is a figure of the final solution output. So after the agents have either accepted or rejected the routes, some of the routes are removed and assigned to those agents, where the rest of the leftover routes go into a pool, upon which phase 2 is implemented, where the savings algorithm and simulated annealing algorithm are run once again, and the final solution output is represented here, where we see the ring-like structure, the hierarchical ring-like structure emanating from the center depot, where we've got the colors blue, green, and red representing routes serviced by trucks, electric vehicles, and motorbikes respectively. You'll be able to note here that since motorbikes have less capacity, in this case a capacity of 2 customers per motorbike, that the red routes service only 2 customers maximum, whereas green and blue routes are able to service a higher capacity. Lastly, I'd like to go over just some of the key performance indicators But before we do that, just touch on the decision variables, that which we're able to change to alter the model's outputs. Namely, those are the vehicle types, which we can change both the proportions of and which vehicle types are included. And we can also change the various proportion of vehicle types. So some of the key performance indexes would be that we want to measure what proportion of career drivers does it start to become unhelpful, what proportion of electric vans is beneficial to reduce CO2, and what is the monetary cost of reducing CO2 of the various vehicle types, assignments, and their corresponding proportions. These are just to name a few. And then finally, some of our preliminary results include various mixed vehicle fleet compositions are already achieving higher quality results than the homogeneous fleet, which is promising. The addition of the career vehicles consistently reduces the operating costs by between at least 10 to 20%. And the model solution executes in polynomial time, which is promising. Thank you.